Welcome to this OpenMP SE21 booth talk. This is the second part of the presentation NUMA in OpenMP. In this second part, I'd like to focus on the support that OpenMP provides to help tune your application for a NUMA architecture. So let's look into more detail what OpenMP provides for you. First of all, tuning for NUMA is all about keeping threads and their data close. I hope that's clear either from the first talk or you already know that. But the goal with NUMA tuning is to make sure that the distance between the threads and the data is as short as possible. In OpenMP, there's a conscious decision has been made to move a thread to the data and not the other way around. You could move data around, but that's a lot more expensive. So the idea is that the data is where it is, and you make sure that the thread that needs that data is close to it. And how do you accomplish that? Well, you do that by using the Affinity constructs. They control where threads execute. They're very powerful, it's a very powerful feature, and this is the first thing to start experimenting with when you want to optimize your application for a NUMA architecture. And you do that through two environment variables. They control the affinity. First of all, OpenMP Places. That's a set-based definition, and that defines a set of locations where you allow threads to execute. And locations could be pretty much anything in the system. Could be the cores, could be sockets, anything you like it to be, you can do. And I'll say a lot more about that on the next slide. For now, I just want to say that you have several choices for the places definitions: threads, core, last level caches, NUMA domains, sockets, or the low level hardware thread ideas that I mentioned in the first part of the talk. A core may or may not have additional hardware threads to support to accelerate the computations, and OpenMP supports using those. The second variable is called procbind, and that controls how you map your thread onto the places. Why would you need that? Well, let's say you have 8 cores in your system and you have 4 threads. How would you execute? Where would you execute those 4 threads? How do you want to map them onto the cores, for example? And there's a choice to be made, and you can do that by setting this environment variable. You have 5 choices. You can set it just to true. In general, I would not recommend that, but what it does is the thread will stay wherever it started executing. So whatever unit, hardware thread, or core it started on, it will stay there. That's a very rigid thing, and like I said, only in a few cases I've seen that to help. I would not recommend it. You can completely disable this kind of binding, where you leave it up to the operating system and the runtime system to make the decisions, or you can select one out of these 3. And I want to spend a little bit more time on that. The choices are primary, close, or spread. Primary means that you want every thread in the team that the primary is part of to execute in the same place. So if the place is a core, you want all those threads running in the core. If it's a socket, you want all the threads running in that same socket where the primary thread is running. Another choice you have is close. What you want is you want threads to be close in terms of the places definition. Places are sets, and there's a list that defines those places. And what you'd like it to be is you want them to be close in terms of that set. The opposite is spread, where you want threads to run in places that are as far apart as possible in terms of the places definition. And I'll show you an example of this shortly. But first I want to spend a little bit more time on talking about these abstract names for the places, because they're very powerful. Once you get the hang of it, you'll appreciate how you can play with those in a very easy way and get threads to execute where you'd like them to be. So when you say threads, you get the number of places equals the number of hardware threads. Every hardware thread gets its own place, and that's the scheduling unit for the scheduler where threads are going to run. If you have 16 hardware threads, you'll get 16 places. Likewise for cores. If you have 16 cores in your system, then you'll get 16 places, and those are candidates for threads to be running. Last level caches is a little bit more complicated, but I think a very powerful feature, where you say, give me all the cores that share the last level cache. And if you know that's going to be beneficial to your algorithm, that's a very powerful choice to make, and it relieves you of a lot of pain to figure it out yourself. So the runtime system will handle that for you. I really think this is a very good addition. It was introduced in later versions of the specification, but I really like it. For the same reason, I like NUMA domain. That's on a higher level. You get a set of cores that not only share memory, but they have the same distance to that memory. So for all threads in the NUMA domain, it means the access time is flat. It's a flat memory domain in that sense. The highest level is sockets, where each socket in the box gets its own place. So if you have a 4-socket system, you'll get 4 places. And here's an example. I'm using 16 OpenMP threads. I define places to be 2 sockets. Note the number there. If you would say sockets, you would get all the sockets in the system. Here I restrict it to 2 sockets. So I have 16 threads and 2 sockets. That begs the question, how are you going to map those threads onto the sockets? Well, what I'm going to do is I'm going to spread them out. And that's, again, keep in mind, that's in terms of the places. I have 2 places now, 2 sockets. And what I want the system to do is find the sockets as far apart as possible. And each socket will execute 8 threads. And presumably that's a good thing for my application. Just wanted to mention before I continue with the rest is this is all at the level of the environment variables. You can go deeper. Where relevant, the OpenMP directives and constructs, they support clauses for NUMA. And often they are implemented as a clause. For example, there's the proc bind clause on the parallel directive. So when a parallel region is created, you can define the binding, like spread or close or whatever. So that's a very nice way. You can also do that if you have multiple regions. If it's nested, you can control that. So a very flexible mechanism at the source code level, just in case the environment variables are not specific enough. You also get runtime functions for the Affinity. And here's a little example code. It's a very simple code just to show you how you can use these. I have a parallel region starting at line 3 and ending at line 9. In that region at line 5, I ask for the thread ID. At line 6, I ask for the place number. That's not the place definition. That's the number in the list of places. Okay, and I print it out. So a very straightforward program. I compile with GCC, I enable OpenMP, and I set the number of threads to 4. My places are the cores, and I tell the system to spread them out, those 4 threads. And this is the output that I get. And what I see, for example, is thread 0 is running on place number 0. Thread number 2 is running on place number 4. And the question is, where are those places in the system? So hold on to that question for a little bit longer, because I'm going to answer that very soon. But before I do that, I want to talk about diagnostics. Because it's really easy to make a mistake in the NUMA setup. You think you got it all figured out, but your places definition is not right, or your binding, or things can go wrong. Your program will run, but the performance may not be optimal. So these diagnostic features are very handy, and I can highly recommend to use them. The first one is OMP display env. That at program startup echoes the settings of all the environment variables, all the values, including the defaults that have been chosen. And that's a great way to verify every setting, but in particular the NUMA settings. You can also get runtime information. That's also very useful, where you display the Affinity information as the program executes. And this is a fairly flexible system. You can even tailor it to your needs. So don't forget about that. These things can really save you in terms of making mistakes. And here's an example. Same example, but now I set display env to verbose. And as a result, I see that my environment variable settings are echoed. So it echoes that the binding has been set to spread. But I also see that in this case, I have 8 places, 8 places, 8 sets. Each set contains 2 elements, because the notation is the starting value, a colon, the number of elements, and an increment. The increment defaults to 1. So the first one, 0, colon 2, means 0, 1. The next one is 2, 3, 4, 5, etc. So that's what I get. And now I know where my threads are actually running, because my program would print out a place number, For example, the first line, thread number 3, is running on place number 6. Well, when you do the counting, you see that's the last one in those squares, those red rectangles. And what you see, the place number 6 consists of hardware thread IDs 12 and 13. So that's where my thread number 3 has been running. You can also see that indeed the use of the places has been spread out because when I run my program, there's a gap between the places that I used, and the system tries to separate them as far as possible. For example, if I would set close, I would get the first 4 sets in that list. So again, I can't stress enough how important this is to help you troubleshoot your NUMA placement and certainly verify that it's doing the right thing. So far, I barely scratched the surface. Most of the things that I talked about have been available in OpenMP for quite a while now, a couple of years. The language committee keeps on adding features because architectures continue to evolve. So OpenMP tries to keep up with that. So my advice is please check the latest standards, and in particular the 5.1, because again, NUMA support continues to expand, and several very nice features have been added since the introduction of the NUMA support. And one thing, but again, there are many more, but one thing I want to call out is there are tailored memory allocators. So you can tune the memory allocation to the needs of the application and what's available in the hardware. For example, you can tell the system, please give me a memory block on a device that has very high bandwidth. Okay. So there's several choices, and it allows you to completely customize the memory behavior versus the application, the needs, and what's available in the hardware. If you're interested in that, I would check out the 5.1 specifications. Start at section 2.13.3. That's about the allocate directive, and that will have pointers to more things that you can do. So start reading that, and it'll sort of unfold automatically. Wrapping things up, I hope that this talk has helped to give you an idea at least what OpenMP provides. The whole topic in itself is very extensive, could be quite a long talk to talk about all the features that are available, but I hope that this gets you started. Remember what I said a little while ago, things like places and procbind are the first thing to start playing with, and you'll be surprised how much difference that can make. I've seen it myself, can make all the difference. So don't forget that, start there and then explore what else is available to tune for your NUMA system. Well, thank you very much. As always, stay tuned. And whenever somebody comes to you and says OpenMP does not scale, please correct that person and say bad OpenMP does not scale. Before I go, there are 2 websites that I want to point out. First of all, there's openmp.org. Openmp.org is your place to go for anything about OpenMP. I would bookmark that site and visit it quite often. There's a lot of things happening around OpenMP. And on this website, you will find the specifications, not only the new ones, but also the older ones. There's a forum where you can ask your questions, and you get a qualified answer. There are other users, but also language committee members that will help out with answering the questions. So a really good place for your OpenMP questions. There are reference guides. Events are announced. There are links to all sorts of videos, other material like books and articles. So it's really a good place to visit quite often, openmp.org. Specific to this event, SE21, there's a website where we will collect all the videos and the PDFs of the slides. So if you want to look at some talks, you want to watch them and download the PDF, just go to this website and you'll find all of them nicely grouped together. For now, enjoy, and again, thank you for your time.